This is Yuting Wang from Shanghai Jiaotong University. I will talk about CompCertELF, a verified compiler that transforms C programs into standard object files. In this case, the ELF object files. CompCertELF also supports separate compilation. I will talk about the techniques behind it and its general implications. This is joint work with Xiangzhe, Pierre, Wilke, and Zhong Shao. The production compilers such as GCC generates object files. However, this is not the case for formally verified compilers. The state-of-the-art of the verified C compiler is CompCert. However, this compilation chain ends at the assembly language. So does most of its extensions. Further compilation of the assembly language into machine code is difficult because CompCert allows an infinite number of frames on the stack. Recently, there's a new extension called the Stack-Aware CompCert, developed by the speaker and his colleagues. It removes this restriction by merging stack frames into a finite and continuous stack. This makes the semantic of CompCert assembling code closer to real assembly programs. However, there's still no verified compiler that can compile from C sources all the way to the standard object file formats. Separate compilation is necessary for organizing large programs. Verified separate compilation is a general approach for verifying the compilation of programs consisting of multiple modules. Suppose a set of source modules can be linked into a source program, and they can be compiled into a set of target modules using the same compiler. Verified separate compilation guarantees that the target modules can also be linked into a program, and this program is a result of compiling the source programs using the same compiler. Then the verification can proceed by proving that the linked source module behaves the same as the linked target module. CompCert adopts this approach because it can entirely reuse the correctness theorem for compiling full programs. In this setting, the same linker is used throughout the compiler passes of CompCert. However, there's no verified compiler that can support verified separate compilation from C programs all the way to the object files. The main difficulty is that the linker at the binary level behaves very differently from the linker at the source level. It is unclear if the framework of verified separate compilation can still work in this setting. We solve those two problems in our paper. First, we have developed the CompCertELF, which, to the best of our knowledge, is the first verified compiler that transforms C programs into a standard object file format. Its key component is a verified assembler that outputs ELF object files. By connecting this assembler with Stack-Aware CompCert, we get CompCertELF. Second, we have extended the verified separate compilation to work for the complete compilation chain of CompCertELF. This results in the first verified compiler that supports separate compilation from C programs all the way to the object files. A technical innovation is a general approach to reconcile two different views of linking, both at the source level and at the binary level. The rest of this talk consists of three parts. We first introduce CompCertELF, and then discuss how to extend the verified separate compilation to the entire passes of CompCertELF. Finally, we present some evaluation and conclude. We first present some background information. CompCert transforms a large subset of C through a sequence of transformations into an architecture-independent language called MAC. From MAC, it further compiles to assembly languages on different architectures. However, the further compilation of those assembly languages to object files relies on external tools and are unverified. Stack-Aware CompCert, as we have discussed before, has fixed the unrealistic stack model of CompCert. It compiles C programs to a language called real ASM, which stands for assembly languages with realistic stack semantics. However, the compilation of real ASM to object files is still not fully verified. CompCertELF extends Stack-Aware CompCert with a verified assembler for real ASM. Its correctness theorem states that if the source program P can be compiled into an ELF object file B, then B should behave the same as P. The verified assembler consists of the following passes. First, some preparation phase. Then, real ASM programs are transformed into an intermediate representation called the relocatable programs by the symbol table generation pass. The relocatable programs are simply an abstract representation of object files. Then the relocation information is generated, and the instructions are encoded into the binary forms. Finally, the relocatable programs are encoded into a sequence of bytes representing ELF object files. Because of the time limits, I will only talk about the most important pass of the verified assembler, which is the symbol table generation pass, which is also relevant for the discussion of verified separate compilation coming later. Symbol table generation is important because it bridges Stack-Aware CompCert and our verified assembler. It performs two tasks. First, it merges internal global variables and functions into separate sections. From this point on, those sections should be treated as indivisible units. Second, it generates a symbol table containing information for linking. In the rest of this talk, we shall refer to this path using CSYMB. We use a running example to illustrate how symbol table generation works. This example will also be used later for the discussion of verified separate compilation. It contains two C files, or C modules. Counter C contains a naive implementation of a counter using a global variable C. It also calls a function for recording the current value of the counter every time it is increased. The record function is implemented in the main module using a global array called RCD. The main function loops to increase the counter until a predefined limit is reached. Note that in this example, both modules contains multiple definitions of internal global variables and internal functions. This makes symbol table generation interesting and also makes the verified separate compilation interesting, as we shall discuss later. C modules are first compiled into real ASM modules and then to relocatable program modules by the symbol table generation. Note that real ASM modules are sets of definitions. For example, the main module is compiled into a real ASM module containing 6 definitions: 2 external functions, 2 internal global variables, and 2 internal functions. The internal global variables are merged into a data section by symbol table generation as an indivisible unit from this point on. Similarly, the internal functions are merged into a code section. Finally, a symbol table is generated. In a similar way, the counter module is also compiled to a relocatable program containing data and code sections and symbol tables in the same way. To verify symbol table generation, we need to prove that the semantics of its source and target programs simulates each other. The key is to show an injection between the memory states exists after the initialization. However, this turns out to be a very difficult task. Take the initialization of the main module as an example. First, the memory for the global variable limit is allocated. Then, the permission is set for this memory block. And then, its data is initialized. Then follows the allocation, set permission, and the initialization of the other global variable. However, in the target language, the memory for those two variables, that is, for the data section, is allocated once and for all. Then follows the initialization for those two global variables individually. To show an injection exists between those two memory states, we need to prove that the reorder of those memory operations has no effect, and also the individual initialization for the target global variables do not interfere with each other. This turns out to require very intricate reasoning about the memory operations. This needs also to be done for the internal functions. We have finished the discussion of CompCertELF using its key paths as an example. Now we talk about how to make it support verified separate compilation. The separate compilation theorem for CompCertELF is illustrated below. Given a set of C modules, assume it can be linked to form a complete C program. Also assume it can be compiled to a set of ELF object files by CompCertELF. Then there should exist an ELF executable file, which is the result of linking of those ELF object files. and this file should behave the same as the linked source program. As we have discussed before, we proved the CompCertELF preserves behaviors, so this problem can be reduced to a commutativity property, which says it doesn't matter if you compile those C modules first and link it later, or you link it first and compile it later, you will reach the same results. However, this commutativity property is difficult to prove because the linker for C programs and the linker for object files behaves very differently. Again, we use our running example to illustrate the problem. In this figure, the yellow regions correspond to global variables and the light blue regions correspond to internal functions. As we have said, the linker at the source level naturally treats models as sets of definitions. Therefore, it is free to rearrange the order of those definitions after linking. We can say that the variable C in counter is inserted into the middle of the variables limits and RCD after linking. Same for internal functions. However, the very purpose of object file format is to allow manipulation of sections without knowing or inspecting their contents. Therefore, after the source modules are compiled into ELF object files, the sections are indivisible black boxes. The linker for object files simply concatenate them together. So it is impossible to insert code or data into the middle of a section. That's why the commutativity fails. Note that this is not a problem particular to CompCertELF, but it's a general problem for any compiler that would like to support verified separate compilation to object files. We propose a solution to this general problem of commutativity. Its realization in CompCertELF is shown here. The commutativity proof for CompCertELF has three parts. The first part reuses the commutativity proof of Stack-Aware CompCert as it is. Then comes the commutativity for symbol table generation, which changes from the linker for CompCert to the linker for object files. After the transition, commutativity is easily established by following the standard pattern. However, the commutativity for symbol table generation is actually not provable for the exact reason we described in the last slide. Now the question is, how could we fix it? The commutativity for symbol table generation is restored using the following ingredients. First, by inserting a syntactical equivalence relation equal P as a vacuous compiler path, we are able to translate from CompCert's linker to a different one called the ordered linker. The idea is that the ordered linker should mimic how the linker for object files work at the assembly level. The syntactic equivalence is simply a permutation of definitions that absorbs the effect of switching the linkers while maintaining commutativity. Because the ordered linker mimics the linker of object files, the commutativity that was broken before is restored after the transition. The extra syntactic equivalence equal R is inserted because the need to revert the effect of the ordered linker on symbol tables. Note that syntactic equivalence preserves program behaviors, therefore they do not affect the correctness of the compilation. We illustrate those ideas concretely using our running example. First, let's look at the transition from CompCert's linker to the ordered linker. Same as the example before, we have the reordering of definitions by the source linker at the assembly level. Because the syntactic equivalents are reflexive, we assume that the modules are unchanged. Then, the ordered linker concatenates definitions like they have already been merged into sections. It is obvious that the linked modules are related by equal P because they are permutations of each other. Now, we need to further translate from the ordered linker to the linker for object files. As before, the definitions in main and counter are compiled into sections by symbol table generation. The sections are then concatenated together as usual. Because the ordered linker mimics how the linker for object files work, the definitions in the linked source and the target programs are in the exact same order. Therefore, the commutativity property is finally restored. For simplicity, we have ignored the discussion of linking symbol tables and the effect of the other syntactic equivalence relation equal R. Now let's talk about the evaluations. The current implementation of CompCertELF has the following limitations. First, It only supports a subset of 32-bit x86 instructions in CompCert's assembly. Second, the ELF files it generates is a subset of the ELF standard, which is sufficient for its compilation. Also, the linker of ELF object files only works for this subset. Finally, it does not support the linking of static symbols. Currently, we are working on a new version of CompCertELF to address those issues. CompCertELF is developed in the Coq proof assistant. It adds an additional of almost 23,000 lines of code on top of Stack-Aware CompCert, and it takes more than 1 person-year to finish. Note that the most complicated proofs are for the symbol table generation and its separate compilation. They account for almost half of the proof effort. We have evaluated the performance of the code compiled using CompCertELF on the benchmark of CompCert. This figure shows the average runtime of 13 rounds of test-C benchmark provided by CompCert. Note that the ELF program output by CompCertELF runs slower by 8.4% on average. However, the sizes of the ELF files generated by CompCertELF are significantly larger, which is 74% larger on average. This concludes our talk. We have developed the CompCertELF, the first verified compiler that transforms C programs into ELF files. We have also proposed a lightweight and general approach for verified separate compilation from C to object files. By applying this idea to CompCertELF, we obtained the first verified compiler that supports separate compilation from C to object files.